right, kids, you made it to the last calculus lesson. I know it can be kind of bittersweet. It's been quite a journey with you guys this year. We started out at the beginning of the year reviewing and then hopping into the first half of calculus, derivatives, and then, of course, we moved to the other branch of calculus, antiderivatives, which we did nearly finish while we were together, and then we've done this application chapter while apart. You guys have really been troopers. I'm really proud of you. This has been quite a unique situation that you'll probably remember for the rest of your life. But I'd like you to finish well. So we have one more thing to do. And it's funny, to figure out what it is, we have to solve this little riddle. So what really was the first calculus thing that we did? What was the first calculus thing? No, I'm not trying to get you to think about the first day of school. That was parametric equations. I was trying to get your attention. But really the first true calculus thing was the second chapter. Did you say it? It was limits. If you retake calculus in college, it's likely that that'll be right near the beginning. You'll feel like that you have done it before. But what we're going to do today is we're going to learn how to find the limit of a special situation. Now, it might be helpful to first just remember what is a limit, because whether it's special or not, a limit will always be the intended height. The limit will always be the intended height. I hope that if you are retaking calculus that you'll feel pretty confident about that idea. So why don't we take a look at this function and the limit as x approaches 0 of this function. Now, if you're squirming a little bit, you might be trying to remember, well, geez, how would I do this? Well, don't forget that the first way that you should always consider finding a limit is by simple substitution. You should always consider what would happen if you would plug in that x value. Now, in this case, you end up with 0 over 0, and I hope that none of you would tell me that that equals, well, that equals anything. It doesn't equal 1. It doesn't equal 0. In fact, it actually just equals an indeterminate. Remember, we said that it determines nothing. It really means to turn around and try something else. Now, what we're going to do to kind of turn around and try something else is we're going to consider, we're going to first look at the graph so that we can remember that it really does have a limit. Now, your eyes should be noticing that hole in the graph. So remember that the y value right there is the limit. And of course, everybody can see that y value is 0. Now, let's try something different. Let's do the derivative. Now, just by the way, I've never shown you this, so this is, again, a new idea. But what I want you to first realize is we're not going to be doing the derivative using the quotient rule. Rather, we're going to actually do the derivative of the numerator and denominator. If you do the derivative of the numerator and denominator, because this is actually a special rule that you're going to learn, you end up getting a simpler function because, of course, you can cancel the 2's. Now, look what happens if you substitute in 0 to this function. Well, first off, you can do it. And second of all, you get an answer because when you substitute in 0, you get 0. Remember, 0 was that same intended height that we saw in that graph a few moments ago. What's this derivative thing? Okay, well, before, again, we go any further, make sure you realize that it's a unique way to use a derivative of a numerator and denominator to end up getting a defined limit. Okay, careful, we're not doing the derivative using the quotient rule, so that means we're not doing like the derivative of the overall function. We're just doing the derivative of the numerator and denominator. So, a little fancy here, we got a square root function. Okay, but what if we want to find its limit? Now, Remember, if you were trying to find this limit, the first thing you should always do is consider substitution. And some simple substitution gives you, once again, 0 over 0. Okay, remember, 0 over 0 is an indeterminate. Now, you're going to learn that if you get an indeterminate, that gives you permission to do this derivative thing. What's the derivative thing? The derivative of the numerator and denominator. Make sure you're thinking about the derivative of square root as a 1/2 exponent. Of course, you bring down the 1/2 exponent, and you subtract from that exponent. So now we have a negative 1/2. Look at the derivative of the bottom. It's nicely a 1. And if you simplify this equation a little bit, the negative exponent mainly, the negative exponent can go to the bottom. Now I should have also put the 1/2 as 1 over 2, but I didn't want to do too much here. So take a look. If you plug in 0, well, you can do it, and you actually get a defined answer. That defined answer is the limit. We've got something going on here. It's called L'Hopital's rule. L'Hopital's rule. And L'Hopital's rule says that if I'm doing the limit of a numerator and denominator, in other words, if I'm doing the limit of a fraction, and you get an indeterminate, you can do the derivative. And those prime signs that you see, F prime, G prime, they stand for the derivative. And the reason I have the letter A in there is because, of course, I'm plugging in A. So we might say it's the derivatives evaluated at A. Now, careful, careful, careful. Don't use this rule unless you get an indeterminate. What's an indeterminate? An indeterminate is something in calculus that we say is like a silly statement, like 0 over 0. Or maybe infinity over infinity. Okay, so L'Hopital's rule, pretty nice, but it only works if you first start with an indeterminate. Okay, so I can do the derivative of the numerator and denominator if I end up with one of these statements. So let's take a look at another example that might use L'Hopital. Here we have the limit as x approaches 0 of the square root of 1 plus x minus 1 minus x over 2 all over x squared. Now, the reason I say that it might use L'Hopital's rule is because you always want to first see what happens when you plug in your x value. Now, here it should be pretty clear that when you plug in 0, you end up getting 1 minus the 1 minus 0 over 0. So, yes, we end up with 0 over 0. Now, that's kind of good news today because that's the new lesson. If we end up getting 0 over 0, which doesn't mean anything, that allows us to do L'Hopital's rule. So it's time to do the derivative. Now we're going to do the derivative of the numerator and denominator. So here we are doing a derivative of square root again. Again, square roots are the same as 1/2 powers. Leave the inside alone and subtract from the exponent. Technically, you would do the derivative of the inside, but that's just going to be 1. Now, the derivative of this minus 1, remember that's just 0, so we don't really need to write that. And then the derivative of this minus x over 2, well, that's kind of like the derivative of a 1/2 x, which is going to end up giving us just a 1/2. Of course, the x disappears since we subtract from that exponent. The derivative of x squared, that's going to be, as it's been many times, 2x. Now, once you do the derivative of the numerator and denominator, it's time to plug in 0 again. Now, when you plug in 0 very carefully, you discover that you get 1/2 times 1 minus 1/2. 1/2 times 1 minus 1/2. And, of course, in the denominator, we're going to end up with 0. Oh, it looks like we're going to get 0 over 0 again. Now, what does this mean? Well, it means that we actually want to do L'Hopital's rule again. You see, you're going to learn that you actually can keep doing L'Hopital until you end up with a determined value with an actual limit. So we do the derivative again, bring down that negative exponent, get negative 1/4, subtract from the exponent, and you get more negative.
The derivative of the denominator now is 2. And as you get better at this, you're going to realize that that's where the real problem is. The problem has been with the denominator all along, since that kept giving us this 0. But now that I've done the derivative twice, my denominator is just a 2. And so when we plug in 0 one more time, well, this time we find out that we do get a determined value. Now, make sure you do the math. This is 1 to the negative 3/2 power. Well, 1 to any power is 1. So we're going to end up with negative 1/4 times 1 over 2. And that's the same as negative 1/8. That is now your actual limit. So we did L'Hopital's rule until we ended up with an indeterminate no more. Until we no more ended up with an indeterminate. So how about the limit as x approaches 0 of the sine of x over x squared? We'll throw a trig function at you here. Well, just like with any limit, the first thing you always want to do is consider a simple substitution. So when we plug in 0, we find out that, well, the sine of 0, now remember the sine of 0 is like asking for the y value at 0 on the unit circle. When I say at 0, I mean at like a 0 rotation. So the y value right here, of course, is 0. That's why the sine of 0 is 0. And it looks like obviously we get 0 in the denominator. So once again, we get an indeterminate, which means you get the green light to use L'Hopital's rule. Now when you do the derivative of the numerator and the derivative of the denominator separately, of course the derivative of sine is cosine, and the derivative of the denominator is 2x. Now, make sure that you always stop and think about plugging in 0 after every step. And don't be too quick to say that, oh, we're going to get 0 over 0 again, because now we're doing the cosine of 0, and the cosine of 0 is like asking for the the x value when you're at a rotation of 0. So, of course, the x value right there is 1. Oh, we get 1 over 0. Oh, 1 over 0. Now, how does that sit with you? 1 over 0. You're saying, I should know what that means. Well, now remember, 1 over 0 is not necessarily undefined. When I say not necessarily, that's because we're talking about limits. So 1 over 0 is actually referring to a certain kind of intended value. So whenever we divide by 0, that means there was going to be a vertical asymptote. And if you have a vertical asymptote, what is the intended value? Well, not knowing what this graph looks like without a calculator, we still know that at a vertical asymptote, we're going to have some type of infinity behavior. So the limit represented by 1 over 0 is infinity. Now, you can also think of this as what is the intended value when I divide by something really small. Well, as I divide by something really small, the answer gets really big, and that's another reason why we're equal to infinity.
This is an excellent opportunity just to stop and remember your limits. You see, if you do evaluation and you plug in and you end up getting 1 over 0 like we just did in this other problem, well, when it comes to limits, remember that that is going to represent infinity. Now, if I plug in and I end up getting 0 over 1, that, of course, will always equal 0, as that's a defined number. What happens if you plug in and you get 1 over infinity? Now, this would be like dividing by a really big number. So if you divide by a really big number, now your intended value gets really, really small. It approaches 0. And, of course, if I plug in and I get the expression infinity over 1, that's referring to an undefined limit. We could say undefined, or we could say infinity, as that would be like the direction that the graph is approaching. So these are 4 expressions from the limit chapter to remember. And of course, don't forget, if you end up with 0 over 0, well, that just means nothing. That means keep using L'Hopital's rule until you get an answer. Same thing with infinity over infinity. That also means use L'Hopital's rule again.
Here's another good limit problem. Notice that x is approaching infinity. and we're going to figure that out for the ln of x over 2 root x. Now, sometimes students aren't as comfortable with the idea of plugging in infinity. That's because you can't really plug it in the traditional sense. It's more of thinking, what does the expression represent when we do the ln of infinity? Meaning, where does the graph go? Now, you can look on a calculator, but basically the ln graph keeps going up and up and up as I go out to infinity. And then if you think of like a square root graph, or even kind of doing the square root of infinity, that also is going to continue to just rise infinitely. So we end up with infinity over infinity. Now, of course, that's just an indeterminate, so that means we're going to do L'Hopital's rule. Now, that gives us permission to do the derivative of the numerator. Of course, the derivative of ln, well, that's 1 over x. And then the derivative of the denominator, once again, is like thinking of a square root. How's that going for you? Bring down the 1/2 and subtract, so we get negative 1/2. Now, a problem like this, it might be worth some time to think about simplifying it before we get too much in the business of trying to evaluate for infinity. First off, these 2's and halves obviously cancel, and with this negative exponent, maybe what I want to do is think of a little mini 1 over, because I kind of want you to see that this fraction now has a numerator and a denominator that's a fraction, and this would be a perfect time to think about how to clean this up, because dividing by a fraction is the same as multiplying by its reciprocal. So we're going to multiply by the reciprocal of the denominator just to change this into one single fraction, which if you do a little bit of interacting here, basically you end up with the ability to subtract the exponents, which leaves you with a negative exponent, x to the negative 1/2, which is the same as 1 over x to the 1/2. Now we have something that we can, so to speak, we can evaluate for infinity. And when you think of 1 over the square root of a half, you're going to end up with the conclusion that that's 1 over infinity. Now, 1 over infinity, oh, that was one of those expressions to recognize from the other screen. And of course, that's going to equal 0, which would be an actual value. In other words, it would be the limit of our original problem. All right, so we got one more example. Here we have the limit of a square root, 4x squared plus 1 over x squared plus 1. Now here x is approaching infinity. If you think of the value of the numerator and denominator, it doesn't really matter that the numerator has that square root. It's still going to increase without bounds, and so is the denominator. So we have an indeterminate, which gives us the green light to use L'Hopital's rule. Now, before I just jump in here and do the derivative of the numerator denominator, I want to bring back up a trick that we used in the last section to kind of allow both the numerator and denominator to be under the square root. First, if I want the denominator to now be under the square root, then I'm going to have to change it. I'm going to have to balance it by introducing a square, which of course now it's still equal to the original problem. The second thing, though, is you might be saying, well, wait, why are you doing this? Well, because it goes to say then that we can think of the limit as, the limit of the fraction sort of independently of the square root that is, that's kind of over top of it. In other words, I can work inside here, do the business of L'Hopital's rule, and then we'll get the square root involved in the last step. So we're going to do the derivative of the numerator, and the nice thing about that is the derivative of the numerator is just an 8x, and it's also pretty easy to do the derivative of the denominator as long as you're sensitive to the chain rule. And don't forget to multiply by the derivative of the inside. And so what happens here is that we get some nice cancellation. If you especially notice the cancellation of all these coefficients, you would determine that we end up with a 2 in the numerator. Of course, the x's cancel out also, so we actually just get a 2. You're saying, Mr. Naylor, what about this square root? Well, just hold on a second, because now I'm going to actually do the limit. which means I think of the value of this expression with infinity, and that actually leads me to a pretty nice place, because 2 over infinity is actually something that is known. Of course, we know that that is equal to 0. Now, we haven't forgotten about that square root, and so the reality here is, all along, I was going to have to do the square roots of whatever it was that we found. And so I can just kind of put the square root back in. Just so you know, the square root really never disappeared altogether, but we're going to put it back in, and we're going to now do the square root of this value, which turns out to still be the same answer. So now we know that the limit is 0. The little square root trick, something that students might not think of, but you're allowed to do that. You're allowed to work inside a square root, do your limit, and then apply the square root to the final answer. In this case, when I applied that square root, I end up again with a limit of 0. So you're ready for your last assignment. This assignment's on paper, and you'll notice that I did give you the answers to the odd on the back. If you want to ask about the even problems, then just give me a shout out. I'll be happy to talk to you about them. Be careful. Don't just kind of mindlessly do the derivative of the numerator and denominator. You always want to first evaluate. You want to plug in with simple substitution and see if you get an indeterminate. If you get an indeterminate, then you can use L'Hopital to come up with a defined value.